Now for these last few problems, we're just going to look at sort of word problem applications for probability distributions and expected value. So let's look at 5. Here a bag of marbles contains 2 gold marbles, 10 silver, and 30 black. You decide to play the following game. A randomly selected marble is drawn from the bag. If it's gold, you win $5. If it's silver, you win $2. But if it's black, you lose $2. And the question is, what's the expected value if you play this game? So what I mean by the expected value is what's the expected value of your total winnings. And now we want to express the losses as negative values, and we'll round our answer to the nearest cent. I'll explain that at the end here. First, let's just decide what our random variable is. So we want the expected value of the winnings. And remember that what we're doing in this section is we're computing the expected value of a random variable. So if you want the expected winnings, you need a random variable that describes your winnings. So I'm going to let the winnings be called x, and let's write down all of the possible outcomes for the winnings. So you could win $5, you could win $2, and you could lose $2. So at this stage, things might be looking pretty good. It might look like we're up $5, but remember that the weightings for each of these is significantly different, right? We're not super likely to win $5. We're much more likely to lose $2. So we need to also include the probability for each of these outcomes. The probability of winning $5 in a single draw is going to be 2 out of 42 because there are 2 golden marbles, and then there are 42 marbles in total. Similarly, the probability of getting $2 would be 10 out of 42 because there are 10 silvers, and the probability of losing $2 in a single game would be 30 out of 42. So that means that the expected winnings would be the expected value of x. For that, we're just going to take the outcome and multiply by its probability, and we'll sum up all of those. So this would be 5 times 2 out of 42, plus 2 times 10 out of 42, plus negative 2 times 30 out of 42. And I plugged this into a calculator already. It ends up coming out to a negative 30 out of 42, which is a negative 71 cents, or a negative 0.71. So maybe one thing that's worth mentioning here is that the expected value of a variable will have the same units as the variable itself. So here, my original variable x was in terms of dollars. So I had a $5 winning, a $2 winning, and a $2 loss. The expected value will have the same units as the original variable. So here I would get a negative 0.71 that's measured in terms of dollars. So what this means is that in the long run, like let's say that you played this game 1,000 times, this expected value is telling you what you would pay on average, like over the course of that whole 1,000 game run per game. So in other words, in the long run, you would expect to be losing 71 cents roughly per play of this game. Now, obviously, that loss can't happen in any individual game, right? Like you have to either win $5 or win $2 or lose $2. But all that this is saying is that in terms of the long-term average, you should expect to be down about 71 cents per play of the game. So if you played this 100 times, then you should expect to lose $71 roughly. Okay, so next let's look at problem 6. It says, suppose you have a random spinner with sides labeled 1, 2, 3, 4, and you spin it once, sorry, that's supposed to be once, record the number and then spin it again. Let x be the sum of the two numbers, and we want to find the probability that x is less than 5. So for this, we again, because we're doing a sum of 2 independent experiments, it might be good to just make a little probability, or not a probability distribution, a little sample space for the outcomes of the spins. So we'll have 1, 2, 3, 4, and 1, 2, 3, 4. Whoops. I don't know why I put 4, 3. So I'll scratch that out. Okay, so this will be our sample space for the 2 spins. So I'm again going to use the row number as the number that you get for your first spin and your column number as the number that you get for your second spin, although it doesn't really matter. So we want x to be the sum of the 2 numbers, and we want the probability that x is less than 5. Now, you could just write each of these as ordered pairs if you wanted to. It would also be fine because we know that we're interested in the sum of the 2 numbers. It would be fine with me if you wanted to just write in each of these cells the corresponding value for x. So here we get a sum of 2. On this diagonal, we get a sum of 3. On this diagonal, we get a sum of 4. And so on. I'm not going to fill in the rest of the table because in the rest of the table, we have x values that are larger than, or at least 5, I should say. So we don't actually care about those. We just want the probability that x is less than 5. So here we want the probability that x is less than 5. And if you wanted to, you could answer this immediately from the table. You could also make a probability distribution separately if you wanted to. The possible sums are 2, 3, 4, 5, and so on, all the way up to 8 as the top sum. And what we can see from this sample space over here is that the probability of getting a 2 is going to be 1 out of 16. Notice that this is a 4x4 table, so there's 16 possibilities in total. The probability of getting a 3 as your sum is 2 out of 16. The probability of getting 4 as a sum is a 3 out of 16, and so on. So if we want the probability of getting something less than 5, that would be the probability that x is 2 plus the probability that x is 3 plus the probability that x is 4. Because this is a strict inequality over here, we don't want to allow x to equal 5. Now notice that we can just add up these probabilities separately because these are disjoint events. You can't get both a 2 and a 3 or both a 3 and a 4. You're going to get either a 2 or separately a 3 or a 4 and so on. So because these are disjoint events, we can just use the addition rule that we talked about in the last section to just add up these probabilities. In other words, if you want the probability of getting one of these outcomes, you just have to add up their corresponding probabilities. So this would be a 1/16 plus a 2/16 plus a 3/16, which ends up coming out to 6/16. So if you want the probability of getting a 2 or a 3 or a 4, you can just add up the probabilities of getting a 2 or a 3 or 4. All right, and notice that in this case, we didn't have to do any sort of multiplication because here we weren't looking for an expected value. We just wanted the probability that this event occurred, the probability of the event x equals 2, 3, or 4. Okay. And lastly, let's look at this one. So here it says in one form of roulette, you bet $1 on even. If one of the positive 18 even numbers comes up, then you get your dollar back plus another $1. So that would be a net winning of $1. If one of the 20 other numbers, so the 18 odd numbers or a 0 or double 0 comes up, then you would lose your $1. And we want to find the expected value for the winnings of the game. So remember, if you want the expected winnings, that means that we're going to take the expectation of a variable that describes the winnings. So I'm going to let x equal the winnings for the game. Now note that x has to be a random variable because we don't know, a priori whether we're going to be winning $1 or losing $1 or whatever. So x is just going to represent the outcome of a single experiment or a single run of the game. Now the possible values for x are a positive 1 if you win. That's a positive net winnings of $1. Or you would lose your $1 if you end up getting a bad spin here. So these are the two possible winnings that you could get. And notice here that their probabilities are a little bit different. The probability that you gain $1 would be 18, because those are the 18 possibilities that you're happy with, out of 38 in total. So 18 out of the 38 positions will give you a win, and 20 out of the 38 total positions would give you a loss. So this would be our probability distribution for the winnings, but this is not what we wanted as our final answer. We wanted the expected winnings. So we want the expectation of the winnings, and that would be each of the outcomes times its corresponding probability. And this would be 18/38 minus 20/38, which would be a -2 out of 38. And if you plug that into a calculator, what you'll get is roughly a -0.05. And remember that the units for the expectation are going to be the same as the units for the original variable. So if winnings was measured in terms of dollars, then the expected winnings will also be measured in terms of dollars. So a -0.05 would correspond to a loss of 5 cents. And remember that what this means is that in the long run, so if you were to play 100 games of roulette, you would expect to be losing this amount on average for each play of the game. So that means that for 100 plays of roulette, you would expect to be down $5. So this, by the way, is something that casinos care about a lot. You will never find a casino game that has a positive expected value. The way that casinos are making their money is that all of their games are designed to have slightly negative expected values, but to sort of entice you with usually more significant winnings than just $1. But the point is that you can have high amounts of winnings with low probabilities and still have a game that has negative expected value. And therefore, in the long run, the players of that game would be expected to lose money. And the law of large numbers just essentially guarantees that the casino, no matter how many people end up winning, will end up having profits at the end of the day. Because essentially this expected value is guaranteed to happen in the long run as sort of the average winnings. So that's the end of this section. Next week we'll talk about Markov chains, which is sort of a more complicated application of probability theory, where we'll get to use matrices a little bit. But remember that this set of topics is not going to be on next week's exam. The first time that you'll see this set of topics on an exam will just be for the